Okay, in this video, we are going to find out the final thing, that is maximum moment under a load. So you had a set of point loads, and let us assume that there is a set of point loads given by W1, W2, W3, W4, and W5. Let us consider there are 5 point loads. Okay, and let us consider our same simply supported span AB of length L, capital L, and as usual, you have a section C. Okay. Now let us consider that. Okay. Now, actually, this section is not relevant here because you are not going to consider it at a span. So I'm just like erasing it. If needed, we can just show it there. Okay. Now you have to calculate what is the how to position this so that there is a absolute maximum moment and under which load this is going to happen. So we don't know that also. So this is as usual, it is moving from left to right, from A to B. The condition for maximum moment under any load is required. So let us assume that we are going to consider how we have to place this load so that we get an absolute maximum under load W2. As an example, I have taken W2. So let us assume that capital R be the resultant of all these set of loads. I am just marking it here. The real case might be different. And let the distance of this R from our chosen load, that is W2, let that distance be small d. Okay, so R to D, distance between R and D. So let distance between the resultant R and load W2 be D. Okay, now R is the resultant of all loads, right? So let its distance from W2 is D, and there should be some relation with the beam also. So let the distance of this R from A, okay, from A, let that distance be, let us consider it as X. Okay. Now we also know that the length of span length is capital L. Okay, with this much mark, let us continue with the derivation or deriving the condition for maximum, absolute maximum under a load. Now, when you do sigma mb equal to 0, what do you get? Sigma mb equal to 0 gives Ra into capital L is equal to resultant into L minus X. Okay, resultant from the figure, resultant into L minus X gives you MB equal to 0. From this, RA is nothing but R into L minus X by capital L. Okay, so therefore, what is the moment? Moment under the load which we have considered W2. Moment under load W2, capital M is equal to, what is it? RA into, okay, there will be RA, if you consider the LHS, RA into X plus D till W2. So RA into X plus D minus this one, R into D. So minus R into D. So I am only considering the LHS part. Okay, it's just M under W2. So substituting, what do you get? RA, RA is in terms of R. So in terms of R, I have R into L minus X by L into X plus D minus R into D. Okay. Simplifying, I'll get R into, or R by L into Lx minus X square plus LD minus XD. Okay. Minus R into D. Now this, let us multiply it by L and divide by L so that you can keep the denominator same. Okay. Let it be like that. Now for what are you trying to find? For moment to be maximum. Moment under the load to be maximum. For moment under load W2 to be maximum. What is the condition? dm by dx should be equal to 0 because we are trying to get a value for x for positioning load W2 to get absolute maximum. So the simplifying or differentiating R by L into L minus 2x, isn't it? L minus 2x plus this will be 0 minus D should be equal to 0, or L minus 2x is equal to D, or 2x is equal to L minus D, which gives x is equal to L minus D whole divided by 2, or x is equal to, let's write L by 2 minus D by 2. So what do you understand from that? L by 2 minus D by 2, or so this is a very important relation where x is nothing but it is the distance of resultant from where? Distance of resultant from the point A, from the starting point of B. Okay. So you can either position your resultant from A, but for us, when you are doing a problem, you will be given a set of train of loads. So it is always better to write in terms of that. So you can distance your selected load W2 from A. So distance of, so it is better to find out that. So distance of W2 from A is nothing but x plus D. So what you have to do is L by 2 minus D by 2 plus D should be enough, which means simplifying you get L by 2 plus D by 2. So distance of W2 from A to get absolute maximum bending moment is this L by 2 plus D by 2. Whatever is the value you are getting, that value, okay, that much distance you have to move your selected load W2 from point A in order to get absolute maximum under that load. Okay, so this is the main condition, but this is easier so that you can place your load in such a distance so that you get absolute maximum moment. So we can conclude that for moment to be maximum under any particular load, the load and the resultant should be equidistant from span. That is, your distance should be either L by 2 minus D by 2 or L by 2 plus D by 2. That is distance of resultant and distance of W2. So it means from the midspan you have to equally you have to place the load and the resultant. Okay. Now, finally, there is one more thing to find out, which also I'll include in this same video. So the last thing is E, that is absolute maximum bending moment. Okay, so absolute maximum bending moment is there. So the ILD ordinate for bending moment is maximum at the center of span, isn't it? At L by 2, you are getting a absolute maximum bending moment. So bending moment will be maximum near the center of span when heavier loads are near the center. So maximum moment always occurs under a V load, under one particular load. So you can conclude that when under this absolute maximum moment occurs under one of the loads, when the resultant of all the loads and the load under consideration are equidistant from the center of B. So you have the same condition which you have derived earlier. So what you will do is for absolute maximum bending moment, what you have to what you can write in sentence is that you can conclude that absolute maximum bending moment happens, okay, when the resultant of the set of loads, when the resultant of set of loads or all the loads and the load under consideration that is in this case it was W2 are equidistant from the center of the beam. Okay, then you can say that there is an absolute maximum bending moment. So this is same, just whatever we have derived, that is this was absolute maximum under a load. Okay, this was absolute maximum under a load. The same condition you can use in order to find absolute maximum bending moment. All you have to do is the set of loads will have a resultant. That resultant and the load under consideration should be equidistant from the center of beam. If you position it like that, what you get as whatever ILD you're drawing and the ordinate you're finding out will give you the absolute maximum bending moment. Okay, I hope it's clear.